Continuing on test 2, I will start this video with problem 6. Find the sum of the series. In other words, we're not testing to see if this converges, we are assuming it does converge, and we want to find the sum. So, well, if it were geometric like part B, we know how to find the sum. Or we had collapsing series where the nth partial sum collapsed into a formula. And then now we have the 5 series that will be given to you on the test, the 5 power series for 1 over 1 minus x, etc. So maybe we could recognize one of those here. And in fact, in part A, I'm thinking of the series, and you would find this on your chart, from k equals 0 to infinity, x to the k over k factorial equals e to the x on minus infinity infinity. And I think of that because of the m factorial in the denominator here. So, well, what's different about this one? There's no x. So, well, x could be, let's see, what would x be? Well, x has to be 1. 1 to the m is 1. And it starts at 1 and not at 0. So this series here has one extra term. When k equals 0, our first term is x to the 0. 1 over 0 factorial is 1. So the term here is 1 when k is 0. And that's not here. So we will say this is e to the x when x is 1, e to the 1, subtracting off the first term of that series. Part B you should recognize as geometric. This is the sum from n equals 1 to infinity of 2 times 1/5 to the n. On the test, a lot of people thought that r was 2/5, but notice the 2 is not being raised to the nth power. You have to look at things a little more carefully. And since the absolute value of r is less than 1, we know that this series converges to the first term. So I plug in n equals 1, and I get 2/5 for my first term, over 1 minus r, 1/5. And multiplying by 5 on the top and bottom, I get 5 minus, or 1/2. Converges to 1/2. On part C, let me change it slightly. Let's just start it at n equals 0 here. Well, you see that 2k plus 1 is not factorial, so this must be arctangent. So let's write the series up here. Arctan x from your chart, the sum from, oh, that should have been a k too, shouldn't it? K. The sum from k equals 0 to infinity, minus 1 to the k, over 2k plus 1, times x to the 2k plus 1 power. That's arctan x, and it converges on the open interval minus 1, 1. And this is a bit of a problem. I don't think anyone in the class noticed it, but what would 1 be here? X would have to be 1. And then if x were equal to 1, we would have minus 1 to the k, 1 to the 2k plus 1 over 2k plus 1. So you're not absolutely sure whether it converges at 1. So this wasn't a good problem for me to write. It does converge at x equals 1, but we didn't prove that in class. It converges at that endpoint. So it converges to arctan 1, which is pi over 4. Problem 7, we are finding intervals of convergence, not worrying about the endpoints. All right, so this first one, remember we are looking at the absolute value of a sub n plus 1. Actually, these are little functions of x now. I could say a sub n plus 1 of x over a sub n of x. We're looking at the ratio of the n plus first term over the nth term. And there's no need to write that down. Just plug in n plus 1 wherever you see n, and remember we're taking absolute value, so you don't need to write the absolute value of minus 1 to the n. That's just 1. So for example here I would write 1 over 5 to the n plus 1, n plus 1 to the fifth. And I have the absolute value of x to the n plus 1. Now I'll invert and multiply, and I have 5 to the n over n to the fifth over 1, and I have the absolute value of x to the n there. This is always going to just turn out to be, if you notice, this is always going to cancel with this, and you're just going to have the absolute value of x left. So you don't really even need to write these powers. They always turn out. Well, no, I guess I take that back. Put them in, because if you had an exponent like 2n plus 1, then it would be different. So keep them in, but they cancel here and give us just the absolute value of x. And let's see, let's rewrite this in a way where you can see the limit. You have 5 to the n over 5 to the n plus 1 gives us, just in the denominator, we have 1 over 5. Then we have n to the fifth over n plus 1 to the fifth, which is n over n plus 1 to the fifth. And we have our x's canceling, and that's the only place we need to put the absolute value signs, because n is a positive integer. There's no need for any other absolute value signs. All right, so let's see, what's the limit? N over n plus 1 goes to 1. 1/5 is a constant. So the limit of this is the absolute value of x over 5. And we need that to be less than 1 in order for the series to converge by the ratio test. So that gives us then the absolute value of x is less than 5, and our interval of convergence is minus 5, 5. Part B, well, we know that sigma r to the k converges when the absolute value of r is less than 1, and that's what this is written like. We have something being raised to the kth power here. So this will converge when the absolute value of 2x minus 1 over 5 in absolute value is less than 1. So that gives us 2x minus 1 is less than 5, multiplying both sides by 5. And now that means that 2x minus 1 is between 5 and minus 5. Adding 1 to each part, we get minus 4 is less than 2x is less than 6, and dividing by 2, we have minus 2 is less than x is less than 3. So our interval of convergence is -2, 3. Part C, we'll use the ratio test. Again, this is a power series centered at -1. So I will take the n plus first term of this series, and I have to have anything that could be negative, I have to have absolute value signs around that factor. So I'll have the absolute value of x plus 1 to the n plus 1 over the quantity n plus 1 times the quantity n plus 1 factorial. And then inverting and multiplying, I have n times n factorial over the absolute value of x plus 1 to the n. All right, well, we know that n factorial cancels a lot with n plus 1 factorial, just leaving us n plus 1. And we know that x plus 1 to the n plus 1 cancels with all of these factors here, leaving us with just one factor of the absolute value of x plus 1. So this is, let's see, we have n over n plus 1 times 1 over n plus 1, n over n plus 1, 1 over n plus 1, and we just have the absolute value of x plus 1 here. Now we're taking the limit as n goes to infinity, and so this just, the absolute value of x plus 1 just remains the absolute value of x plus 1, but this factor goes to 0, and this factor goes to 1. So the limit then is 1 times 0 times the absolute value of x plus 1. So it goes to 0 regardless of x. And that tells us that our interval of convergence is the whole real line, minus infinity, infinity. Part D, again, we use the ratio test. It's another power series. And I'll take the m plus 1 term, or I'll just use n. I'll have the absolute value of minus 3 to the m plus 1 is 3 to the m plus 1, I'll use m, times the absolute value of x to the m plus 1 over m plus 1 plus 1, so that's m plus 2. Notice I took the absolute value, and I only needed absolute value signs on the x. Now invert and multiply. M plus 1, we know that's positive, over the absolute value of minus 3 to the m is just 3 to the m, times the absolute value of x to the m. So now we cancel if we can. Well, the m plus 1 over the m plus 2, nothing cancels there, so let's write that as a factor. And 3 to the m plus 1 cancels with 3 to the m, leaving us just one factor of 3 on the top. And just like before, the absolute value of x to the m cancels here and just leaves us with one factor of x on the top. So we have m plus 1 over m plus 2. We have a factor of 3 times the absolute value of x left on the top. Now, as m goes to infinity, m plus 1 over m plus 2 goes to 1. So taking the limit here, we get the limit is 3 times the absolute value of x. And that limit has to be less than 1 in order to get convergence. So that would mean that the absolute value of x is less than 1/3, and our interval of convergence is minus 1/3, 1/3. Problem number 8 I did on the video for section 11.7 Taylor series. I'll just do it really quickly here so you don't have to go back to that video. We need to either see g of x as a result of function composition with another function for which we do know the Taylor series or the power series, or we need to see it as the integral or derivative of a function for which we know the power series. Now, this is not going to be the square of a series. You can't square a series. Just think, if you square a sum of 3 things, you have 6 terms. We can't think about squaring series at this point. So in this one, I think what we did was to recognize this as a derivative. This is minus 1/2 times the derivative with respect to x of 1 over 1 plus x squared. Now if you don't recall this, go back and look. It's the very first problem I did in the last lecture video. And recognizing it as that, well, we know a series for 1 over 1 plus x squared. That's on your chart. And this would be then minus 1/2, the derivative with respect to x, and you might as well just write it out as 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus, and so on. Or you could use the series notation too. That's just fine. Either way it works out. So now, well, let's differentiate term by term. We know that this is a convergent series, and we can differentiate term by term. So the derivative of 0 is 1, and we get minus 2x plus 4x cubed minus 6x to the 5th plus 8x to the 7th minus ... And we could multiply in the negative 1/2, and that will change the sign all the way across and divide by 2. So we get x minus 2x cubed plus 3x to the 5th minus 4x to the 7th plus, and so on. So that would be the answer. If you want to see that with sigma notation, you can go back to the video that I did. Now this one will be multiplying a power of x to the series for cosine 3x, which we would of course obtain from the series for cosine x. So let's write down our series that's on your chart. Cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus, and so on. Now those of you who are using the summation notation, I think that you're doing fine. I didn't see anybody that was using it doing it improperly. So I'm going to stick to this for sake of not making these videos so long. All right, well there's cosine x. So cosine 3x, well, we plug 3x into cosine. Well, we're going to plug 3x in for x everywhere in the series. So the cosine of 3x is 1 minus, now it's 3, I'll go ahead and put it in parentheses, and then we're going to have to take them off, plus 3x to the 4th over 4 factorial minus 3x to the 6th. Remember, every step you show, if it's correct, you get some partial credit. So why not show this step, because then if you mess up removing the parentheses, I will know that you at least knew what to do. Okay, so we plug 3x in for x. Now you need to multiply all of that by x squared. So let's write x squared times that will be x squared times this. But I can't multiply that x squared across and get the standard form for a power series unless I remove the parentheses from the 3x's, because I'm going to just add 2 to the exponent on x. I don't want to add 2 to the exponent on 3. So we'll take one more step here. This is equal to x squared times 1 minus 3 squared over 2 factorial times x squared plus 3 to the 4th over 4 factorial times x to the 4th minus 3 to the 6th over 6 factorial times x to the 6th plus 3 to the 8th over 8 factorial x to the 8th minus. And now you just add 2 to the exponent on x. And of course x squared times 1, so we get x squared minus 3 squared over 2 factorial x to the 4th plus 3 to the 4th over 4 factorial x to the 6th minus, and so on. So there's the answer to that one. That was much easier than the first one, because the first one in number 8 you had to recognize it as a derivative. Problem 9, it said use series to determine the limit. So we need to find a power series representation for the function 1 minus e to the x all over x. Well, we know the power series for e to the x, so 1 minus e to the x is going to be very simple. E to the x is equal to the sum x to the n over n factorial from n equals 0 to infinity. So 1 minus that, well, let's write it out. Let's not use summation notation. It's going to be 1 minus, and then we'll write the series for e to the x. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and so on. Now, to subtract 1 minus all of that, a lot of you did not bring the minus sign across the entire sum. Look down here, let me just show you in case you did that. If you had 1 minus a plus b plus c, you're going to write it as 1 minus a minus b minus c. You bring the minus 1 across. It's using the distributive property of multiplication over addition. So let's do that. So 1 minus e to the x is equal to, writing it in standard form for a series, would be 1 minus 1 is 0, minus x squared over 2 factorial minus x cubed over 3 factorial minus x to the 4th over 4 factorial minus. And now we want to divide that by x. So in other words, I'm going to multiply this series here by 1 over x, or x to the minus 1. And we get then minus 1 minus, subtracting 1 from the exponent, x over 2 factorial minus x squared over 3 factorial minus x cubed over 3 factorial minus, so on. Okay, now it said use that series to determine the limit as x approaches 0. Well, as x approaches 0, every one of these terms from there on out is 0 when you plug 0 in for x. And so our limit is minus 1. So we would say the limit of this is, I'll just write arrow minus 1 here. Now it did say to check using L'Hopital's rule, and that was part of our study in Calc 2, was using L'Hopital's rule. So let's see how we would do that. Our function is 1 minus e to the x over x. And we notice before you use L'Hopital's rule, you have to make sure that the top and bottom are both becoming infinite or both going to 0. And we see that the numerator is going to minus infinity and the denominator is going to infinity, so we may use L'Hopital's rule. And the derivative of the top would be minus e to the x. The derivative of the bottom is 1. And now, as x approaches 0, oh, you guys, I'm so sorry. I was letting x go to infinity back here when I was talking. X is going to 0. So e to the 0 is 1, and the numerator is going to 0, and x is going to 0. And so since we have 0 over 0, we may use L'Hopital's rule. And now, sorry, I just get all these, we're always letting things go to infinity in these series, and I made a mistake. All right, so 0 over 0 qualifies, and we take the derivatives. And now as x approaches 0, this approaches e to the 0 minus e to the 0, which is minus 1. And so our limit is minus 1 over 1. And we checked our answer with L'Hopital's